Okay, so we were doing bonds,
Mhm.
and these are the files that we have. Let's see. So yeah, in the last meeting, we simulated, I think, two atoms
Mhm.
placed at certain distance and
Mhm.
harmonic bond,
Mhm.
right?
Mhm.
The bond
Mhm.
potential looked
Mhm.
like this, harmonic bond potential. So this is what it looked like. I mean, like
Yes.
this.
Mhm.
It's a
Mhm.
parabola.
Mhm.
Today, what we want to do is we want to model the same bond
Mhm.
using Morse potential, like this one,
Oh,
the
okay.
green,
Mhm.
yeah, the green one. So the harmonic
Mhm.
approximation does not allow you to soften the bond as you keep stretching the
Mhm.
bond, whereas Morse potential allows you that, see, bond softening.
Mhm.
Um,
What do you mean by bond softening exactly?
that means, look at this. So for
Mhm.
instance, here on the left side, you can see that both of them are performing like in the same manner,
Yeah, symmetry.
right? But on the
Mhm.
right side, as you stretch bonds,
Mhm.
harmonic potential requires infinite amount of energy, huge amount of
Mhm.
energy to keep stretching it, right?
Mhm. Mhm.
But your Morse potential does not require you infinite amount of energy, right?
Mhm.
Right? I think
Mhm.
it can allow you to even break bond. So as you keep
Mhm.
stretching after a certain point,
Mhm.
so the energy required to keep stretching increases. After a certain point, it just breaks,
Mhm. Okay.
right?
So reaching at potential energy of D1 means
Yeah,
it is breaking, right?
yeah.
Why
Well,
it
in
should
this
reach
figure,
why it should
and
reach to one?
why should it reach to one? No, this is, I think, normalized units.
Okay, okay.
So D probably means something by divided by something probably. Okay.
Mhm.
Yeah, the energy can be different for different bonds, of course. But the idea is that this is like a general form of those two equations. D
Mhm.
is probably a parameter, maybe in Morse potential
Mhm.
expression. Let's just say. So
Mhm.
we'll go for LAMMPS org manual and we search for Morse bond. Yeah. Look for Morse bond and here maybe this D is determines the depth of the potential well.
Mhm.
Equilibrium depth of the potential well. Probably that is what that DE represents. Yeah. So this height is probably the from 0 to 1. Right? So 0 is here.
Mhm.
If you look at some other maybe images like this one, it has no numbers. But that's the idea. Okay, that's
Mhm.
the idea that this one, the harmonic one, is modeling a spring.
Mhm.
Okay. But the Morse one is more allows you the bond softening on the right side as you keep stretching.
Okay, but what is the actual reality? What actually the atoms obey? Will they obey harmonic or will they obey mass? How
So
should we
Morse
choose?
potential, yeah. If you look at the expression, it's a little more expensive to calculate. You have more parameters to evaluate.
Mhm. Mhm.
Uh, and it's not a straightforward R minus R naught multiplied by K over 2 squared. R minus R naught is squared multiplied by K over 2. It's not straightforward. This expression to evaluate takes more compute time. So if the property of interest, your property of interest,
Mhm.
can be modeled by a simple harmonic expression, go with that.
Mhm.
Um, yeah, go with that. If you do not expect any bond softening, unnecessary, bond
Mhm.
stretching,
Mhm.
then you don't have
Mhm.
to waste compute time modeling Morse bond.
Mhm.
You can just choose your harmonic bond and
Mhm.
yeah, use that. It's way much faster. In the same 24 hours of compute time, you can probably
Mhm.
extract more nanoseconds of simulation data,
Mhm.
right? So in reality, both of these are good approximations of bond stretching, but
Mhm.
are they exact? I don't
Mhm.
know. They do the job. They do the
Mhm.
job. They allow you to reproduce properties of interest very well. But are they reality? I don't know.
Mhm.
They're good approximation of reality
Okay.
that I can tell you. Yeah.
Mhm. Okay. Yeah.
Okay.
Okay.
So let's go to the file. Let's look at the file harmonic LMP. Here is the file.
You
So
just
last
created now? No,
no
last
no
time
no
we
no.
created. Okay. Okay.
Uh this one is harmonic bonds. Last time we did this
Mm.
already actually.
Okay. Okay. Okay.
Uh,
Okay.
let me show you what we did last time first. It's just more like a revision thing. OVITO. Come on. Oh, my molecule. First, let's load that. And then on top of it, display radius. I'm going to change it to a little less, maybe like 0.5 for this guy and this guy also 0.5. And now you can see the bond, right? This is the molecule file that we had written. Okay.
Mm. Mm.
Let me show you that. Not that. My molecule. Here. This is the file that we had written last time.
Okay.
Two atoms, one bond,
Mm.
everything else, right? And so this is like the same mymolecule.txt file that we have loaded here,
Mm.
right? And yeah, on top of it, then we simulated this system. This has no frames. You can see that it's just a data
Mm.
file,
Great.
molecular structure file. Then we simulated this file using this, setting, atom style molecular, reading mymolecule.txt, basically this file. And then we have set harmonic potential. You can see that, right? And the constants that are required to solve that harmonic expression, right? And this is just settings that you control for your own convenience. How often do you want to print thermodata to the console? How often do you want to print thermodata to your log file and everything else, basically. So we have done this one already.
Mm.
Okay.
So
Let me
we
show you
just
the.
need,
Mhm.
I mean, we will just change that statement of
Yeah.
harmonic to.
So we are transitioning from modeling the bond with harmonic to modeling the bond with Morse
Mm.
potential. Okay.
Mm.
So okay, let me show you from the beginning because this is important. Um, First, I'm going to load my data structure file. You can see OVITO, load the data structure file. Okay. And this is what it looks like. I want to be able to see the bond.
Mm.
So right now, these two atoms are represented with uh, larger radius. So I'm going to select here particle types and then the first atom. And then here, display radius. It's visible, yeah. Display radius. In that, I'm going to select, just reduce the size of the radius of that
Mm.
atom. Okay. Hit enter. And now you can see the display has changed, right?
Mm. Mm.
You can see the box dimensional box boundaries also. Now I'm going to
Mm.
take the second argon and also change that to 0.5 so that you can
Mm.
see the bonds that
Mm.
exist in your data structure file.
Mm. Mm.
Yes. And then I'm going to go to add modifications at the top right corner here. Add modifications, and then there is load trajectory. See that?
Mm.
Load
Mm.
trajectory.
Mm. Mm.
So our OVITO already has understanding of the molecular topology. By topology, I mean bonds, angles, and everything else, how atoms are connected.
Mm.
Right? OVITO knows about it because we have just loaded that, right?
Mm. Mm.
Now, what I'm going to do is I'm going to load the trajectory file on top of it, okay? On top of the data structure file, okay? Um, and here is the file that will allow you to select the trajectory that you want to load. So let's go locate the place. Oh, come on. Hmm. Oh, we have it in a Scratch and Dr. Alok bond, and I think cool dump file dot alok. This is the trajectory file.
Okay.
This was the data file. We ran it through the simulation, and then the simulation generated a trajectory file of this name, cool dump file dot alok. You can also see that here. Look at the name of the trajectory file that we have specified in our LAMMPS. So that is the trajectory file that was generated by running this through the simulation, right? Okay, I'm just going to load that. And it just loaded 50 frames. Do you see that? Initially, it was 0 frame because there was one structure. Now we have frames, 50 of them. And since the OVITO already knew the topology of our system, because the topology is specified here, which atom is bonded to which one. And on top of that, we loaded trajectory file. The trajectory inherits that topology. Okay. So if I go to the second frame, you will see that the bond remains there. Although the trajectory file does not have that bond, I think. If it has, great. If it does not, we have loaded that through the data file. Anyways, let's go and look at it. I'm just going to play it. So you can see that, bond is stretching.
Okay.
Yeah, that's the harmonic potential.
Okay.
That's what happens. The bond will never break. Yeah, the atoms will just keep translating around that main position. All right, so that's what we did last time.
I have a question here. So the figure which we were talking just in the starting of the class, the U shape, that is the potential well, okay, the potential well figure. So can we generate a potential well figure from the OVITO simulations? Like you show that the bond is vibrating.
Yeah, of
At a,
course, of course. So look at this. Let's go back to this one. I'll show you with harmonic. That's probably easier. Harmonic bond. Look at this. This is the expression, right? That potential represents this equation, right? Some constant. All you have to do is change the R value, right? And R naught is fixed, equilibrium bond length. As you change R, E changes, right? You just have to plot this equation. That's it, nothing else.
Yeah, no, that I got it. But does it actually, we can get that same thing from OVITO application? That's
It's
what happens.
not it's not the OVITO that facilitates you plotting. It's
Okay,
it's
okay.
the trajectory file. In the trajectory file, you can see that the two atoms, translate.
Translate.
So in each frame, the R values are fixed, right? The distance between the two atoms, this R
It's fixed.
is is fixed from a frame. So what you have to do is just take the XYZ, calculate the Euclidean distance between two atoms, okay? And that goes in this equation R, right? And R naught is the equilibrium bond length, which you have specified, okay? Let us see what we have specified. This is the place. We'll go to less harmonic LMP. And you can see the equilibrium bond length that we have specified is 1.2. So the R value comes from your frame by calculating Euclidean distance, right? The distance changes, so the R changes. R naught is 1.2 that you have specified already in your LAMMPS file, right? 1.2. And the K value also you have specified to be 50, right? So you can see that all you need from the trajectory file is the Euclidean distance of at any given frame, right? And you just have to, plug in the R naught and K value there and just plot that. That's it. You will get that same thing. Yeah,
No,
no
I'm
problem.
interested to see that when it will be breaking. So can the OVITO simulation show us that since the bond is vibrating at for a 50 frame, suppose if we increase the frame time to 500, let's say 500. So at that 500 time, will that bond break? Will it break or will it not break? That is my
So
question.
our model is this, right? And you can see that this model, if you plot, looks like
Mm.
this, right?
Yes, you.
So as you increase as you stress further and
Mm,
further those
mm,
atoms, what
mm,
happens is you move towards the right side of that potential well, right?
okay.
Towards the
Yes.
right side. And as you
Mm,
move towards the right side, the
mm,
y-axis, the E value,
mm,
energy
mm,
value,
mm,
goes to infinite. You have seen that, right? It touches to
mm.
infinite, which means
Yes.
for you to stress them further as you move, far and far, as these
Mm,
atoms move far and far. To move them
mm.
further, the energy required would be huge.
Huge. Mm.
So it will never be possible to break that bond
Okay. Mm.
if you're modeling with this expression,
Harmonic.
right? The potential energy does not allow you to do that. So LAMMPS
Mm,
cannot do that. LAMMPS is just
mm.
a calculator,
Okay. Okay.
a
Mm,
smart calculator.
mm,
So yeah,
okay.
if you're modeling your bond with this,
Mm,
it's never going to happen, of course.
okay. Mm,
Yeah,
okay.
right?
Mm,
Yeah.
yes.
All right. So
Mm,
today
mm,
we'll just take the same data
mm,
file, and
mm.
today we will try modeling with Morse potential. This was the objective. We have seen these
Yeah.
commands. We have done two items. I'm sorry, say that?
I was just saying that because we already had a code for harmonic one, so we can just change those lines in between just
Yes.
now.
That is exactly what we are going to do. We have two atoms connected by Morse bond. That's what we will do today. And then if
Mhm.
time permits, we will do a simple water-like molecule with two bonds, of course, OH-OH, and the angle
Yeah, in
HOH.
the next class.
We can start
Yeah.
today probably because the harm Morse bond modeling is not going to take long actually.
Okay, okay, okay. That makes sense.
Yes. So
Mm,
here you can see that we are in
mm,
Dr. Alok
mm, mm,
bonds directory. Okay.
mm, mm,
In the bonds directory, we have these files.
mm,
I do not want to mix harmonic with Morse. So what I'm
mm,
going to do is I'm going to create two directories. Okay. I'm sorry. I'm going to create a harmonic directory
mm,
and I'm going to create Morse. You can see that the two directories are now available, Morse and harmonic, right?
mm,
And I know that these files belong to harmonic. So what I'm going to
mm.
do is I'm going to just move all these files into this directory, okay? So that we can
Harmonic.
keep the project structure clean. Going to move all the txt files
Mm,
into harmonic.
mm,
You can see that the txt files have moved, like this file has probably
mm,
moved to
mm,
this,
mm, mm,
right? If we look at the harmonic, yep, this file has moved. We
mm,
also need to move other files, like for instance, this one. So move harmonic.lmp to this directory and then move cool dump as well to this directory and then move log lamps also to this directory. Now it looks way much better. All the files
mm.
are in this directory and this one is cleaned. Okay, let me show you what harmonic looks like. Here, these are the files that are available in harmonic directory. Right, I am listing files in harmonic directory. And if you look at the files in this directory, there are none, right? Because we did not really create any or move
Mm,
any.
mm,
So let's go to Morse, and it has nothing, no files. For Morse, well, to simulate Morse bond, we are going to write a data file and a LAMMPS file. So
mm,
we are just going to borrow those two files from harmonic directory and then make changes to that. So I'm going to copy. Let me show you the directory structure, maybe like tree. Oh, that's a lot, probably tree, depth 2. Ah, that's too much. Mm, It doesn't show. Anyways, do you understand? Like here is what the directory structure looks like. We have Dr. Alok, and then we have harmonic, and then we have Morse, and we are currently in Morse, right? So we need to copy the files. So for that, we have to go up by one directory first, and then harmonic, and within that, there are these files. We need to copy this data file into current directory. The dot represents current directory. Two dots, they represent parent directory. Okay, and now you can see that that file has been copied from harmonic to Morse. In the same manner, we are going to copy the LAMMPS file. Okay, let's see, we got my molecule. This is the file that we need to copy to current directory. There it is. Now we have both of them, right? Uh, Also, I'm going to rename this to Morse. Yeah, let's just keep it small. No, probably not a good idea. Morse.lmp. Harmonic. Yeah. So what happens is move the contents of this file into this basically. Oops. And now we have only Morse. So that represents correct name at least. The data file will not change, right? Because the structure is same. We just have to change the force model. Right. So let's go and edit this Morse file here. Bond style, we will change that to Morse. Let's look at this actually. What LAMMPS command is here. Bond style Morse, exactly that is how we are supposed to write. So that is written. And then we are going to need coefficients, right? Coefficient is going to be slightly different. This time you have to provide D value, alpha value, and R naught value as well. There are three constants that we need to provide now. In the harmonic, we have to provide only K and R naught, those two, right? So this time we have to provide three of these. Let me see what parameters I'm going to use. Mm, Yeah, this is the constant. So the constants that I'm going to use are 20, 2.0, and 1.20. Yep. So that should be your equilibrium bond distance, 1.20. That is the distance that we want to maintain between those two atoms. Um, and this is probably alpha value and then the D value. Okay. Let's just save them.
What is
And
the
then
first value?
let's see.
One.
Oh, that represents the bond type. There is only
Okay,
one
okay.
bond,
Okay.
right? So there is only one bond, and for that bond, these are the parameters. Now let's start running it. LAMMPS input file is Morse, and it says invalid attributes fz in dump custom command. Oh, so this is of course incorrect. There should not be O, because that's just this variable is not recognized by LAMMPS. It knows fx, it knows fy, it knows fz, it does not know fzo. So that is, I don't know how I incorrected that.
So will you not make a new dump file for this Morse song?
Say it again.
I mean, I'm asking, will you not make a new dump file?
We will
Uh,
make.
uh,
This is a new dump file actually. We can rename it, no problem. But you know
okay.
that harmonic files, files from harmonic directory are in that directory,
Hmm.
right?
Okay.
And if we create another file with the same name, it doesn't matter because it's in separate directory, right?
Separate directory. Okay.
Yeah, it's managed, no problem. I mean, we can rename it. We can call it cool Morse dump file.alloc, no problem. Okay. Um, the weird name that I'm giving you here is to help you understand that you can name it whatever you want. It's
cool down file is just a name, right? It is not
yeah,
a
it's just a
keyword.
name.
Cool is a
Yeah,
not.
yeah. Often the problem when you use Windows is that the file names matter a lot. Like .pdf means it will open in Acrobat.
Mm,
.html means it will open up in Chrome.
mm,
.mp3 means it will open up in, a program that can read MP3 file.
mm,
But here we are working with text files, so it doesn't
mm,
matter what text, name you
mm,
give it, what extension you
mm,
give it. And so to help you understand that, but we'll start renaming them better.
mm,
So I corrected that, removed
mm,
FZO because that is
mm,
not recognized a
mm,
variable. And then I'm gonna rename it to something nice. Let's just call it
mm,
Morse.trj. That's the way to write it, trj. So in the future that this is a trajectory file.
mm,
Right? And also let's just start following the right things. Instead of my molecule, I'm just going to call it um, molecule dot data. Yep, that's it. So that's a data structure file. Save it and then run the, okay, there is problem. It says that cannot open the file. Yes, that's true. That file does not exist. We know that,
yes. Mm, yeah.
right? Let's go to Morse and move that my molecule into molecule dot data. Okay. Now that file exists, it should work. And it worked. It finished running.
Mm,
You can see. And now we have more trajectory file available. Let's load it.
mm, mm.
Before loading the trajectory file, oh, let's just load trajectory file. Yeah, why not? Oops, sorry about that. You can see there is no bond between these two atoms, right?
Right?
Yeah, yeah. So that happens because your trajectory file does not have topology information, which atom is bonded to which one.
Mm,
Trajectory
mm,
file does not have that information,
mm,
right? So if you want to look at bonds as well, here is what you should do. You should write OVITO. First, you should load the topology file, which is molecule data. Okay. Let's go to particle and again reduce that to 0.5.
Oh, and then we will be externally loading your trajectory.
Yes, yes. On top of the topology file, we'll load trajectory file. Add modifications. That should be load trajectory. And then this guy, Morse trajectory, open. Now you can see there are 50 frames here, right? And here you go. That's what it looks like. Well, you may not be able to appreciate the motions modeled by Morse. It may look exactly like the other one.
Yes.
Um, but if you plot the values, from trajectory file, you will
Mm.
see that difference. We can
Mm.
do that in next lesson, actually, not a problem.
Yes, we
We
can.
can, yeah,
We,
we'll
yeah, we
just,
can. We will
we'll,
concentrate on this aspect, and we can do what up next in the next class. Okay. So yeah, we can discuss and yeah. So how to get the data from there? What are the things OVITO can provide us?
wait, say that
We
again,
see
what
when
question?
what are the things OVITO can provide us now? Since we have uploaded the trajectory, we are running this simulations. So what is the next steps? How to get the data?
What data?
What data means? What is the energy loss? Something like that.
Uh, all those things are not provided by OVITO. You can look at it. OVITO only facilitates you visualization of your
Okay.
data file, of the
Mm.
trajectory file that you have. All
Okay.
the values are in your trajectory file in the data file.
Mm. Okay.
OVITO is just an intermediator between your file
Mm.
and you. So you can look
Mm.
at the file basically, file information.
Mm.
Like here, look at this one. Okay. All information is here. OVITO is
Mm.
just reading it and displaying it in nice format for you. That's it.
Mm. Mm.
Right? This is trajectory file, so it has information of how the configuration evolves over time, right? Like you can see, time is step 0. This is your configuration, right?
Okay.
Atom 1 has XYZ value, sorry, XYZ values, these, and atom 2, it can't be that here, XYZ values, and then XYZ values. In the next time step, the box size remains the same, but the XYZ value change, you can see that, right? These are the XYZ value.
Yeah.
Atom ID, that is
Mm.
column 1, XYZ, the
Okay.
next three columns.
Just now, since we have some time, why
Mhm.
can we not include? Will it be taking more time for that? So I was just wanted to include more items in this box and see what
Yeah,
happens.
you can include
Mo-
more atoms.
mm,
Yes. When you include one more atom, like we have two atom, and then you include one more atom. Do you want the
No,
third
no,
atom to be
no, no. I'm not. I'm telling you we can include more items like 10, 20 items.
yeah.
And so is it like two atoms will be one like atoms will be only be having a pair? Is it like that? Or multiple atoms can have bonds in between them?
Multiple atoms can have bond. That's how you make a
Like are
molecule.
we
Yes.
modeling H2 or what we are trying to model like we are in
Right
so
here,
uh,
it's
for
just a toy
Yamaka
model. It's
for a
just a
model.
toy model
Okay.
to help you understand how you can model
Okay.
two different kinds of
So
bonds and
two.
build
Okay. So
on
it is
top of
like if
it.
we can say we are about because we have two atoms, we can say we are modeling O2 oxygen. No?
Hmm.
So we
Not
can also
oxygen. It's just a toy. It doesn't have to
mm,
be hydrogen oxygen because,
okay. Mhm,
it's just a toy model.
mhm.
You
So
can
how
call
it
it
will be
hydrogen oxygen.
how it will be looking if we have more atoms in between? Will they interact?
That you have to decide. That LAMMPS is just a smart calculator. You have
Okay.
to tell
Okay.
LAMMPS how to model the
Mm,
interaction between atoms and what kind
mm,
of interactions exist,
mm,
right? So for instance, you already have in the system two atoms that are bonded. If you introduce a third atom,
mm,
okay, and there are two choices that you can make. One, the third atom is not bonded to these.
mm,
The second option is third atom is bonded to these,
mm,
right? When the third atom is non-bonded,
mm,
you have to tell LAMMPS how to model interaction between this atom, and this
mm.
atom,
This atom.
right? Non-bonded interaction. Like,
Mm,
so for non-bonded interaction, you would
mm,
probably include electrostatics, van der Waals,
mm,
right? If you're going with van der Waals forces, to model van der Waals forces, there are LJ forms,
mm,
right?
mm,
Um, and you have to describe to LAMMPS that
mm,
this atom will interact with this and this with LJ equation,
okay.
right? And if you're going to say that LJ equation is what you're supposed to use to model interaction between these guys, then you also have to tell LAMMPS LJ parameters for all of them, right? Right? And if you choose to just bond, this atom with the other two, you can do that as well. Just that you have to then describe. Now you will have two bond types, like this bond and then this bond, right?
Mm,
There will be two different bond types.
mm.
Okay. Yeah. So
So, mm, is it compulsory to, like, for example, for a bonded atoms, is it compulsory to use only one type of interaction? For example, in this case, we are using Morse. So, can we not include harmonic and Morse both?
both, of course, you can do that, no problem. You just have to specify the parameters for those equations to be solved.
Okay. And
Yeah,
also,
you're the
can we
one.
Mhm. Also can we not have the non-bonded interaction to see whether, for example, for a bonded atoms, we are using the harmonic one,
Mhm.
but we say that there can be some interaction using van der Waals. So we will
Yeah.
use the LJ potential laws.
Hmm.
So I'm just seeing
Let's do that.
complicating it to include more interaction for the
Yeah.
same code.
Yeah, I'm gonna go ahead and create a new directory called Morse LJ.
Hmm.
And let's go to Morse. LJ. Uh, we'll copy those two files from the top Morse directory, molecule data to here, and Morse.lmp to here. Now we have these two files, we'll build on top of it. Okay. First, we need to bring that third atom into the system, right?
No,
So
no,
let's
no, I'm
go.
not, not talking about third atom. I'm just talking that we already had a two atom and we are using harmonic interaction. I just wanted to add LJ equations in the same code just after Morse. Will this
You
work?
can still do that. You can still do that, no problem. But
Hmm,
think about it. These
hmm,
two atoms are
hmm,
interacting with the bond, right?
hmm, hmm, hmm,
And these are very like close atoms,
hmm, hmm,
right? Uh, Technically, they might have, LJ interaction, but
hmm,
that's not really needed. We would expect the energy of these two
hmm.
atoms to be modeled by bond itself.
Got
Yeah. So when we simulate like larger systems,
Hmm,
we often exclude
hmm,
LJ interaction between 1, 2, 3, and 4 atoms, okay?
hmm, hmm,
Because we uh, assume
hmm,
and also probably that the bond,
hmm,
angle, dihedral, and improper.
hmm,
Those
hmm.
equations are already capturing the all the energy. If you
Okay.
add LJ on top of it, that means you're
Hmm,
overestimating the energies,
hmm,
right?
okay.
So specifically in LAMMPS, there's a
Hmm,
command, a special bonds command,
hmm,
which
hmm,
allows you to exclude LJ interaction between the bonded 1,
hmm,
2, 1, 3, 1, 4 bonded atoms.
hmm. Okay. Yeah. Maybe in the future classes we will see all the complicated
Yeah, yeah, of
diagrams.
course.
Yeah.
So right now, actually, we have enough times that we can do the angle problem.
Okay. Okay.
Yeah, give me a minute. I'll just move to the other lab.
So you are alone in the lab today?
Uh, I was Neil has
Okay.
just arrived. I'll just stop sharing this screen so that I can join from the other one.
Yes. Yes.
Okay, let's go. Share screen. You can probably see my screen now.
Yes. Yes.
Perfect. We'll try modeling a soy water molecule. First, I need to log into my SP computer. Can you see like is it visible? Like the text are
Yeah.
okay?
Yeah. Yeah.
Okay. Okay. Ouch. Make directory. Let's just call it angle. We have no file here, so what I'm going to do is I'm going to go ahead and copy the files, the two files, data file and the LAMMPS file from previous work, okay? So that we can build on top of it. Let's go to bond, harmonic. and we have harmonic LMP file, which we can bring here. Now we have that file. Other than that, we also should bring up the molecule file, which is my molecule here. Perfect. Now we have those two files, a data file and a LAMMPS file. Okay, let's rename them properly. We'll call it just maybe like, I'll just call it input.lamps file. Okay, and move my molecule into molecule dot data file. Oops. Okay, perfect. Let's go ahead and edit the data file first. If we want three atoms, if we want three atoms, like a water-like molecule, um, you can imagine, let's just talk about water molecule. It's not exactly water molecules because I don't know the exact parameters for them. So we'll just make up some numbers. Okay. For a water-like molecule, we'll have three atoms. We will have two atoms, OH and OH. We will have, say, only two atom types. We can just say that, two atom types. Both of these hydrogen, we'll consider them to be, type 1. Okay. And oxygen is of type 2. Okay. So we got three atoms, two bonds, two atom types, and one bond type. We know that we have two bonds, but both of these bonds will be similar chemically because both of these are OH bonds, right? Yeah, so we can just say one bond type. Also, we have to mention here we have one angle, right? And we have to mention here one angle types. Okay. And we can keep the box size same simulation box. For masses, we should probably choose, let's just say that type 1 is oxygen. For oxygen, let's get exact numbers. Oxygen molecular weight mass 16 point, this is 32 OOT. No, now that we need this one. I'll just give it 16.00. And then for 2, which is hydrogen, 1.008, I guess. So that's basically masses, right? You can see at the top we have specified 3 atoms, right? But we have specified only 2 atom types, right? So 2 atom types, since we have specified, we need to specify mass for both the atom types. Atom type 1 will be your oxygen, atom type 2 will be your hydrogen. So the second and third atoms, both of them are type 2, and so for both of them, this mass will be applied. Does that make sense? All right, so let's go to atom. We'll add one more here. This is probably, let's just call it oxygen. This one, I'm not sure. Do you remember what was this column, second column? Let's see. Atom, molecule, type. No, the columns under atoms, molecular, LAMMPS data file. The first column is atom ID, the second column is molecule ID. All right. If it's a molecule ID, then it's just single molecule that we are modeling, right? So we can just say 1. This is our first molecule. And the third column has to be atom type. So atom type 2. The first is oxygen, type 1. And for that, this is the mass that will be applied. The second and third, both of them are hydrogen, and for that, this is the mass that will be applied, right? So now I need to write the coordinates for those. And to be honest, we don't have to write the coordinates again. Let me mention that. Um, this data file can be generated in many ways. Since we are doing toy models, I'm showing you these by writing them myself so that you can just get a feeling for it. You don't have to do it yourself, okay? There are softwares and tools for that. A toy water molecule. So I imagine that the oxygen is sitting at the origin, okay? The hydrogen is going to be in the positive x direction, one of them. The other is the other guy will be in negative x direction, okay? So that is how I imagine my water molecule to be a water-like molecule. So let's just say my oxygen is at the origin, okay, 0.0. And this is my first hydrogen. So the OS bond is, I think, probably 0.96. So
It is the bond length.
yes, OS bond length. No, I'm not giving it the bond length. Uh, how do I? Let me bring up pen and paper, okay? All right. So this is what I imagine my molecule to look, water-like molecule to be. At the origin, we have oxygen, and on the two sides, we have hydrogen in the y
Yes.
dimension. Okay. So
Okay.
at the origin for oxygen, I'm just going to say 0, 0, 0, right? And at 0.96 distance, in the y direction, I'm going to have this hydrogen. So for that, I'm not sure exactly what x and y coordinate I should put. I'm just going to put it 0.96 and 0.00, 0.9600. So in x dimension, I'm saying 0.96. And
What?
say that?
And y direction? Or do you
Yeah,
not write them?
yes. Interestingly, the initial coordinates, here is how I'm going to do right now. My water molecule
Anyway,
is going,
you will be putting an angle also, no?
yeah. So that will fix. This is what my water molecule is going to look like for now. Okay, let's just try that. Okay.
Yeah, I understand. Yes.
Yeah. So we're just going to do 0.96 and negative 0.96.
Hmm.
Well, that will be too much. I think the bond length is going to be very long then. We can just reduce it to 4.8 probably. 4.8 and 4.8. So that the, no, wait. It has to be 0.96 because there is oxygen in the middle. 0.96 and 0.96. Yep, this looks good. We have the bonds. It says bond type 1 is between 1 and 2. And the second bond is going to be, again, the same bond type because both bonds are of the same type. And that is going to be between, again, 1 and 3. Because the first one is oxygen, right? This is oxygen, right? You see that? One atom type, atom 1 means oxygen here, right? Both of
Do
these are
you,
oxygen. See, the oxygen is bonded to the second atom, which is hydrogen. And then the same oxygen is also bonded to the third atom, which is again the hydrogen. Does that make sense?
yes.
Okay. So yeah, this is bonds. And then we are also going to need to have angles. For angles, we have only one type. Okay. oh sorry, this is serial number, and then this is the type of angle, and then we have angle is between which atoms.
So
Let me see exactly. I think we have to say 1 is in the center, so probably 2, 1, 3, maybe like that, 2, 1, 3. Okay. Um, Let me copy this whole thing and look at it in OVITO so we can see how the molecule looks like. Okay. Nanomolecule dot data. Here, it did not load for some reason. Oh, there should be one. Now it should work, hopefully. Yep. See the difference? Earlier in my data file, I did not have one free line, empty line at the top. Okay, now I have one empty line. That is the only difference that was there. And because of that, OVITO could not read, right? So all I did is I went to the same data file and I inserted one empty line at the top. You can have a comment also, whatever you want to name it, like,
why is it like that?
yes, that understanding is very important. OVITO is in the background, maybe C++ or Python files, right?
Yes.
Or Fortran or whatever that is, I don't know the codes. In the background, it is basically some code, and that code, a code which is going to read your data file, is very rigid. It's very rigid. I mean, some flexibility is definitely there. When you say dot data file, it will just go ahead and see which code it should use to read your data file. And your data file has to follow certain format. Like the first line has to be a comment, the second line has to tell you how many items it has. That is how the code
Oh, so
reads. The parsing of your data file is done
okay.
by your code, and that code expects your data file to be of certain format. It's not an
Sorry.
AI that it can read and understand. It's a rigidly written C++ file that is reading your file, right?
Okay.
And that is
Okay.
why data format is very important. All right, so yeah, Ovito probably guessed that this guy is going to be oxygen and these two are hydrogen. Ovito guessed it based on the mass, probably atomic mass. So this is what it looks like right now, right? So we know our data file is correct. I mean, not exactly correct to be honest.
I have a question here. We didn't,
Mhm.
we have not included the radius of the C. Neither we have included the radius of hydrogen. How did Ovito knew that or they are using just a random radius just for simulation? Is it like
Right,
that?
right. So we are doing classical modeling.
Mm.
Classical modeling. In classical modeling, we assume that each atom is a point particle. And a point particle, it does not have to have a radius or diameter. It's a point. All it has is XYZ value. And now on the atom, you can associate more values like charge on an atom that you can associate with it. But it's a
But
point particle. It's
earlier you have reduced the radius ISO, huh?
yes. So that
For
was not
2.5.
part of classical modeling.
Okay.
That was the part of visualization, how to look at your atoms.
Okay.
So that is different from your simulation. Like
Okay.
here, I can just go select particle, and here, well, this is on Mac, so it allows me to do it differently. Look, you see that? I can change the radius. It's just
But
Ovito is
still,
doing,
how did, like, for example, even if for visual, if we see just now, the red color atom is slightly larger than the white color atom. So how
yeah,
did
that's
this Oviedo determine that it should be presented like this? Has they used the mass to determine the radius?
exactly. It has
Okay.
used mass to figure out that this should be oxygen, and so it has
Oh.
to be bigger than the hydrogen. And there are default radius values that it will adopt to, and it
Mm.
will show you according to that. Okay, but
Oh.
it's all part of visualization. It's all part
Mm.
of the way you want to look at it. It does
Mm.
not change your modeling or science
Mm.
behind.
Mm.
Yes, in the end, each of these atoms are still point particles. They do
Mm.
not necessarily have, this
Mm.
looking. It's just something that allows you to just understand that
Mm.
better.
Mm.
In the end, what we have is XYZ value for this, this, and this. And then our file knows that these two are bonded and these two are bonded. That's it.
Mm.
Okay. We did not specify color for an oxygen atom. We did not specify radius. Those things are coming from OVITO so that you can understand it better. Yeah. All right. So this is what it looks like. Let's go back. Um, Save this guy. And now we need to change our input file so that we can simulate the angle stuff. Right? Units good, dimensions good, boundary good, random style, molecular, read file. I think we have changed the name, so let's just, this one is probably mol.data file now. So we have bond style harmonic, bond coefficient harmonic again. So for angle also, we need to specify this time. Right? Let's just say we are going to use harmonic, and now we are going to use angle coefficient. Since we have defined that angle style will be modeled using this equation,
Mm.
okay? This time it's going to be k by 2 theta minus theta at equilibrium whole squared.
Which
This
one
time
is
it's
that?
not going to be r.
Oh, so it
This,
does. Oh, I got it. Theta
right?
not actually. Theta minus theta
Yeah,
not.
yeah. So instantaneous theta value and the theta that you want to maintain, okay? And angle of type 1, because there is only one type of angle that we have defined,
Mm.
right? And some number, k value, and the angle that you want to maintain. Let's just say we want to maintain 104 theta, okay? And rest probably we can keep the same. Uh, let's see, we'll try running it. Um, we have some problem. It says dump. Oh no, I
Oh,
did not
that's the
change that.
same.
Hmm.
Yeah, I think it is coming from the original file. And
Yeah,
also there is some.
I
No
should go and
problem.
change that. No, it's a good thing actually. These errors will help you understand how to troubleshoot them. So this one ran pretty fast. You can see that, right? For 50 frames, it must have generated. Now what we will do is here, cool dump file dot allo. This is the trajectory file, right? We'll just take this trajectory file, we'll copy it to my place so that we can look at it.
So
Um,
we'll again load that trajectory. And
yeah, we need to look at that trajectory file, right? So we'll just copy that. I need to figure out where I want to copy that. Oh, come on.
oh,
Home
so you
Krishna
don't you okay?
scratch.
So your laptop doesn't have allow.
No, wait, it's in my other Ubuntu machine. So I need to copy that file. Krishna at 10.222.72.244 and home Krishna scratch Dr. Alok, and then no, we have angles. Let me look at the directory name exactly what that is. Angle with capital A, and in that we have the file, this one. We want to copy that right here. Let's see if that works. Okay, this is copied. So we have already loaded the data file. Let's load on top of it the trajectory file, okay? I'm just going to drag and drop here.
Oh,
Oh, no, wait. Let's just cancel. I have to load this way actually. Load trajectory. I'm not sure where
In
that
the model,
is.
in the modifications. Modification.
Okay, there it is. And then open the file, documents. This should have it here and open. Now we have 50 more frames, you can see. And let's just go. Clear, this is very bad starting point. Uh, it's just simulating those two. Okay.
Length.
So how do we get the bond to be right? I think we should change the molecule data file. I want to lift it up, so I should give it some y value. Okay, let's just try giving it some y value of, I don't know, 0 point maybe 5. And then this guy is going to be also 0 0.5 maybe. Okay. And here I have to change so that I can look at it. Right? Okay, this is better. Definitely better. Can probably give it like a little more angle, right? And then reload this guy. Yep, looks slightly better. And then I'm gonna just go ahead and edit this guy again a little bit. I have no clue the distances and everything else. I'm just hoping my harmonic potential will bring it to the right value. And yeah, let's just kill these things first and then go ahead and open the data file. Oh, also we need to simulate this. We need to run the simulation again. There it is. The new simulation is ready. And then we should copy the trajectory file. Copied that. Okay. Okay, here is our water toy molecule. Not like that. Where is dump here? Modification. Load file. Choose the file. This one. Okay. This one looks slightly better.
I think
Yeah.
the angle is also vibrating, and
Yeah. Yeah.
the length is also changed.
Both will happen. Both will happen because both the
Okay,
equations
okay.
are being solved. Yes. If you want to see that actually, um, look at these columns. These columns are
Mm,
being read, being
mm.
calculated by OVITO. So
Oh yeah,
bonds,
there is some.
angles, particles. We can select this. This is atom selector tool, and this is the bond distance calculation tool, okay? Or even angle calculation. I can then select the atom and then this guy, and then, well, these two. Let's look at that, okay? We want to
Mm,
see how the distance between these two varies. You can
mm,
see that OVITO is right now reading your XYZ value of those two atoms and calculating Euclidean distance, and that is being printed here.
mm,
So this information is not in the trajectory file. The
mm,
trajectory file has the fundamental information, which is XYZ coordinates of atoms.
mm,
This information is being calculated by OVITO for you,
mm, mm.
okay? If you look at that, clearly that is changing, right? And it is actually mostly 1.2, which is the distance that we wanted it to be, I think.
Actually,
Or, say that.
I have some doubt. In the
Mm-hmm.
original that molecule file, not molecule file, where we have used the harmonic. So
LAMMPS
in that
input file.
LAMMPS input file, so in that harmonic equation, no, sorry, was it Morse?
No, we use harmonic. If you
Okay,
want to look at it,
we just
here. Wait, no,
so
not this one. Here. We used
so here,
harmonic bond.
okay, I got it. I think, oh, okay. So both
Uh,
both are there, bonds and angles both are there. Okay.
yeah,
Mm,
right. And you can
Oh,
see that the bond length that we wanted to maintain is 1.2. And so if you look at this number, it mostly is
approximately
around that.
outside.
Yeah, we can change that to be 0.96 if we want to simulate, really water-like
Can
molecule.
can you change to some arbitrary number? Let's see what will happen. For
Distance?
example,
I told
1.0.
you this. No, no, no. This is, you mean you want to change that here?
Let's change to 10. No, not
Wait,
1.10.
1 nanometer?
Yeah, let's see will the with the crash.
No, it will
What
not
it
crash. That I can tell you, it will not crash. That's my understanding. Oh, it says the problem is, yes, the problem is that the oxygen is at the center and then 1 nanometer goes out of your box.
okay.
So what we
So
can do
still,
is,
if we increase the box length, then still we are able to, right? Hmm. So we could have no problem in changing the
uh,
bond.
there's another problem. It says bond atoms are again missing. What could be the reason? Shenzhen is pretty big already. Um, input file. Oh, the bond coefficient. Yeah, we want to maintain a bond length of 10. And it says it starts running, but then the problem is it says bond atoms 1 and 2 missing on processor 0 at step number 9. Up to step number 9, it's okay, but step number 10, it misses the bond. Oh, this is a good opportunity for me to help you understand something interesting actually. So you see the problem occurs in step number 9, right? Are you there?
Mhm, yes.
The problem occurs in step number 9, and the processor 0 is solving our system,
Mm,
and it says that the bond atoms 1 and 2, these two are missing on processor. That means processor has no idea where these two atoms went. Okay,
mm,
at step number 9. So, and if you look at the input file,
mm,
oops, bad, 2 nano. You can look at it and you see that my trajectory file is being written every 10 steps, right?
mm.
So if I want, I know that problem occurs in step number 9. So what I'm going to do is I'm going to dump the trajectory every step so that I can look at it. What is going wrong?
Mm.
Okay, and then run it again. Same problem occurs, of course. And then copy the trajectory file and load that. Mm, there you go. We have 9 frames here. Oh, sorry. The box is definitely hopefully bigger. Let's see. If you want to look at that simulation cell, mm, where is that information? All right, no problem. There it is. You can see that it's 20, 20, 20. 10 in the negative, 10 in the positive. So box dimension is definitely bigger. We know that. Oh yeah. Our data file has bond distance between these two guys very small, right?
Mm.
And the moment integration proceeds, our force field wants to keep this distance like very huge,
Mm.
like 1 nanometer away. Let's look at the next frame. Increasing. This is what is going to happen. See that,
Oh, and
right?
what happens at the ninth step? Does it crosses the box?
It crosses the boundary. And then after that, these two atoms are just missing, and processor has no clue where these two went. So the bond length is the atoms are moving very fast. That's the problem. I think we can resolve it probably. We are already using PBC boundary conditions. Let me see.
What is PVC bound?
Sorry, the boundaries are fixed. Do you see that?
Okay, okay. Fixed.
Which
Oh,
means yeah.
can we make it
So
flexible also?
yes, there are also these are the things that we read in theory. So I changed it to P, right? P means periodic, which means if atom crosses from one side, it will reappear on the other side.
Okay.
But this will be problematic because these are bonded atoms. These are not non-bonded atoms. For non-bonded atoms, it would make sense.
It
For
will be
bonded atoms, it makes no sense. I mean, like,
how we
I don't
can.
know. Let's run. Yeah, we are doing some crazy simulations. Like, really, it has no connection with reality whatsoever.
Mm,
But for the sake of understanding and how it works, let's do that.
mm.
So I ran the simulation and then I copied the trajectory file to my Mac. Okay, I'm gonna load the data file and then trajectory file again. Okay. You see that? Did you see
Oh,
it
we
ran? It,
ran
of course.
500. Mm.
Let's go to step number 8. Now, since the boundary conditions are such that the atoms moving out of boundary are allowed to come from the other side, in the next step, you can see it's just
Can you
like
play it
almost,
once?
yeah, you won't be able to see. So I'm doing it slowly. The next, see that? The atoms have not really crossed the boundary probably. Yep. Here is what happens. The angle is kicking in. The angle is kicking in. So probably angle is getting slow. So they were going out, but then they're also coming back in.
Because we have fixed the angle, right?
Yep. And now you
Oh,
can see this.
oh, they have
What
jumped out.
happens? This atom is probably going out of the boundary.
Mm.
And so it will this is the weird thing. Yeah. This is happening all because of the periodic boundary conditions. Okay. The atom that crosses the boundary will reappear on the other side, from the other side.
Mm. Yeah, I got it. I was just curious to see how it reacts to these changes.
Yeah, I understand. I mean,
Not
when
a
I was
problem.
learning all these things, I had all these things. Same questions. Okay.
Not a problem. Yeah, I understand today's tutorial. So yeah, let's what we will be learning next.
You tell me, what do you want to learn next?
No, you, how can I am clueless. What should
Okay,
be
so
okay? Yeah, so I finally we have to head towards polymer bonding. So, but we'll go slow and build the concept. So, what powers? What is the most powerful step?
yes. So for the next session, we could do you still are you still interested in looking at the harmonic potential and Morse potential? What we can do is we can read the trajectory file, take XYZ values, calculate Euclidean distance, and plot those two energies, Morse
Mm-hmm.
energy and do you still want to do that?
Today's class?
No, next.
Yes, yes, yes.
Okay,
Yeah,
then
we
we will
can.
start off with that. Okay, we'll start off with that. We'll try. Do you want to do it with Python or C++?
C++. Oh, Python.
Okay,
Any? I am not sure, confident in Python. But it's okay. Can do MATLAB. MATLAB. Can we do in
yeah, we
MATLAB?
can. I don't have MATLAB. I'll have to
Okay.
reinstall that.
Okay, no problem. Yeah. Even for the
So
sake of understanding, is can do any.
we'll start. We'll use Python then. We'll use Python. And we'll plot both of them and we'll look at them. And in the next lesson, actually, we can actually simulate a water system.
Sure.
Okay. Yeah. So
Yeah,
it's going to
multiple
be
items, huh?
similar.
Mm.
Yeah.
Multiple items in the bond. Okay.
Yeah. We'll take similar. We'll construct a single water molecule file,
Mm. Uh,
and our lamps will replicate that water molecule file into say 1,000 water molecules. And then our lamps will also fill those 1,000 water molecules in the simulation box. Okay, so this tutorial will show you how you can write a molecule file for single molecule and then fill that in your box however number of times you want, right? Yeah, so that we can learn.
Okay, we can. So